In this video, I will review the topic of instant centers, and we'll see how to calculate velocities of various bodies of in a mechanism using the instant centers uh, found for that mechanism. So we basically defined instant centers as points on the mechanism. These are points common to two bodies, and we said that velocity of the instant center as seen from either body is the same. The important thing to note is that it is an instant center, which means at any given configuration or any point of time, we see that these are going to the instant center is going to have the same velocity from either body. The next instant, when the mechanism has changed to a different configuration or a different position, the instant center might change. And we said that if there are n bodies in the system or n links in the system, we can choose two at a time, and we get n times n minus 1 divided by 2 number of ICs. So for a 4 bar mechanism, we can have an instant center for, so this is body 2, this is link 1, which is ground, this is 3 and 4. So we can have instant center between 1 2, 1 3, 1 4, 2 3, 2 4, and 3 4. These are 6, which is the same as 4 times 4 minus 1 by 2, which is the number of instant centers that this system can have. Out of these, the simplest thing to consider is if two bodies have a common point like this point is bound to have the same absolute velocity. When I'm looking at the velocity of point A from body 2 versus velocity of point A as seen through the rotation of body 3, it has to be the same. So velocity of A in body 2 is going to be velocity of A in body 3. This does not mean this is not same as VB with respect. I mean, it's not the same as VA with respect to B. That is not the case. This is VA with respect to V plus V of B with respect to O4. We know O4 velocity is same as O2, so we don't have to go back from here to VO4 with respect to O2. This is 0. So VA3 here refers to the absolute velocity as seen from body 3, which means, let's say I was standing here on the second link or on the third link, and you were standing here on the, I was standing on 3 and you're standing on 2, then when you look at A and when I look at A, I know how fast I am moving. So the absolute velocity of point A as seen by me would be same as absolute velocity of A as seen by you. And that makes physical sense because you cannot have A moving in two directions as seen from two different ground planes, or um, as seen from two different bodies. So so in that manner, we can identify that all these revolute joints are essentially instant centers. This is one. This is the instant center 2 comma 3. This is instant center 1 comma 2. This is instant center 1 comma 4, and this is instant center 3 comma 4. So we have 1 2, 1 4, 3 4, and 2 3 is done. So what we are uh, left with are instant centers I1 3 and 2 4, which are unknown, and we can identify these using Kennedy's rule. Kennedy's rule says if you take three bodies, you know that there can be three instant centers because it is 3 times 3 minus 1 over 2 is 3 instant centers. These three instance centers lie on a straight line. This is the rule. It's also called Aron-Hall-Kennedy theorem. We will not look at the proof for this at this point. We will try to identify uh, the the instance centers 1, 3, and 2, 4 using this. So let's say these are the this is the forward mechanism. This is link 1, 2, 3, and 4. So what we do for this is we try to draw or we try to mark all the bodies on a circle, and then we start connecting the ones which we know. So we know 1, 2, we know 2, 3, we know 3, 4, and we know 1, 4. And we are trying to identify, let's say we are trying to identify 1, 3. So we can then consider a three bodies, 1, 2, and 3. So we can consider these three bodies and say that I12, I23, and I13 have to lie on the same straight line. So we know this is I12, this is I23, and there's a line joining these two. So we can extend that line and say that I13 has to be on this line. Similarly, then next we can consider a uh, next we can consider this set of bodies and say that I12, I uh, uh, I14, I34, and I13 have to lie on the same straight line. So this is 1, 4, this is 3, 4, and then I can draw a straight line and say that the remaining I13 has to be on this line as well. So the only possible solution is this point. So at this given instant, when the angles are specifically these theta 2, theta 3, and theta 4, this has to be I13. We can similarly find I24. So these are the four links, and we have this triangle 1, 2, 3, 4. This time we know these, we also know this. We're trying to find I24, so we can consider first this set of bodies, and then next we can possibly consider the other uh, combination 2, 3, 4. So we get we know 2, 3, we know 3, 4. So we must have the IC going on, staying on some line like this. So this should I24 should be on this. Then we can take 1, 2 and 1, 4 and say that I14 has to be on this as well. I24 has to be on this as well. And that's the only solution here. This will be I24. What this essentially means is this body 2 and this body 4. So by the way, we have now identified all 6 of the instance centers for this instant. We know we can say from here this link is having a certain rotation, and this link is also having a certain rotation. So these both are rotating about this point specifically. And similarly, in the previous case, you could say that uh, they are both rotating to with as this point as the center, this as the center. So these two are doing a rotation like this at that instant. Obviously, we know that the ground plane is, or the ground link is not going to move anymore, which is essentially why I13 has to have an equal and opposite kind of a rotation so that this holds true, which means that this instance center will keep changing in position. Similarly, this instance center will keep changing position. So we have, let's say, a 4 bar with a coupler of this shape, and then this link is in this position. We are trying to find uh, the velocity of this point. So we can first mark the instant centers. This is one instant center, this is I13. And then what we know is, with respect to this instant center, the velocity of this point A should be same as the velocity as seen from this instant center. These are all on the same straight line. So what I mean by that is A should have the same velocity as part of link 3 as well as link 2 as well as part of link 3. So as a part of link 2, given that this is rotating at omega 2, we'll use the standard convention of A, B, and C being the link lengths here, and this is D. So we know that the velocity of point A as a part of link 2 is equal to A omega 2 in magnitude. And this is orthogonal like this in direction. So we know this already. And when we say A as a part of link 3 should have the same velocity, we can then draw a line from instant center 1, 3 and form this kind of a triangle. We know that the whole body 3 is now rotating with respect to this instant center I13. So we can say that omega 3 times A I13 should be equal to the velocity of point A with respect to this I13. And so we can directly find the omega 3 to be V of A divided by, this is the magnitude, A I13. But we already know that VA is A omega 2. In addition to that, we also can say that once we have found omega 3, we can find the velocity of this point, velocity of B. This should be equal to B I13 times omega 3. And similarly, once we know B, we also know that it is a point on body 4. So this should also be equal to uh, D times omega 4. And so we can directly obtain omega 4 equals VB divided by D, which is equal to B I13 divided by D times omega 3, which I can then write as B I13 divided by D times A omega 2 divided by A I13. So you see, based on the simple position analysis of, I mean, we have now got instant distances from the instant centers to these points A and B, which we can find from the positions, and we just have to do this calculation to obtain omega 4 and this calculation to obtain omega 3. So that makes it easier in cases when the instant centers are accessible on the page where you have drawn this. Sometimes when the links are, the two links under consideration or the two bodies under considerations are somewhat parallel, the instant centers end up tending towards infinity, and that's not at all a convenient place to use instant center based velocity analysis. The other purely graphical way to read off the values of these velocities of VB, for example, would be taking AI I13 and BI13 as the radius, and just drawing a curve which goes and touches this line. So now this distance is B equivalent, this distance is equivalent to BI13, and you can use similar triangles and drop a perpendicular to this point and say this is the velocity of point B. You can also consider this radius. Maybe I'll draw this in green just to distinguish them. This radius of this point C, let's say, and then take this arc, join it here, then drop a perpendicular and say this is the velocity of the point on the coupler we see. The essential idea in all of this is that based on the definition of the instant center, the links which share the instant center will exactly have identical velocity at that point. And so all the points on link 1, which is the ground link, have zero velocity in the global coordinates. And the I13 is, as a part of this link, must also have a zero velocity at this instant. If I13 has zero velocity, then it can be considered as a fixed pivot for the link 3, which is in pure rotation with respect to link 1. The next moment when this position changes, the I13 would have moved to a different position, and so the link 3 would be rotating about a different instant center.